So, okay, let's start. The first speaker is Yi Yu. He's from Shandong University, and the first is the title is measurement of the longitudinal and the transverse spins transfer to lambda and anti-lambda hyperons in the polarized proton-proton collision. So Yi, can you try? Hi, good to see you. Can you try to
nice to see you. Okay. Now can you see my slides?
Yes, we can see your slides. Okay.
Okay. Good morning or evening. I'm very happy to be here to share our analysis. The longitudinal and transverse has been transferred to lambda hyperons in the 200 GeV polarized PP clearance. And my name is Yi Yu from Shandong University. So in this talk, I will firstly introduce the physics motivation on the measurements, and I will introduce how we measure the longitudinal and transverse in transfer and present the measured results. And the last is my summary. So the decomposition of the proton spin, the naive quark model tells you us that the proton is composed of 3 valence quarks, namely 2 U quarks and 1 D quarks. The proton spin is given by 3 quarks according to the quark model, with 3 spin 1/2 quark. 1/2 quarks gives you a spin 1/2 of the spin 1/2 of the proton. However, an experiment conducted at in the late 1980s by the European muon collaboration tells us that the quark contribution to the proton spin is consistent with 0 at that time. This result caused the so-called spin crisis or spin puzzle of the proton spin. And now we know that the spin of the proton is composed of the spin of quarks and the spin of the gluons and also their orbital angular momentum. And for the longitudinal spin structure of the proton, which means the polarization direction of the proton is along its momentum direction, we use the holistic distributions to describe its internal structures. The holistic distributions at the leading order can be defined as the difference of the parton density, which is parallel to the proton spin and the anti-parallel to the proton spin. The right plot shows you the global analysis of the holistic distributions of different partons. And as we can see from the first row, the holistic distributions of valence quarks have been constrained well. However, for C quarks, in particular, in the bottom row, the strand quark, there is a large uncertainties still here. And when the proton beam is transversely polarized, namely its polarization direction is perpendicular to its momentum direction, we can use the transversity to describe its spin structure. Transversity is one of the leading trace parton distributions, but its definition, we can also at the leading order is defined as the difference of the density with the parton spin parallel and anti-parallel to the proton spin. And currently, even for U quark and D quark, as shown on the right plot, there are poor experimental constraints. And currently, we do not have information about the strand quark contribution. Because of its chiral-ordered nature, we cannot access the transversity in the inclusive DIS experiment. And one of the possible way to access it is by measuring the transverse spin transfer of the hyperons in both the DIS experiment and the proton-proton collisions. So in the proton-proton collisions, the longitudinal spin transfer, I will first focus on this. And firstly, I will demonstrate why we choose lambda. Firstly, because as we all know that the lambda is weak decay. We can measure its polarization while it's weak decay through the angular distribution of the decayed proton at the lambda rest frame. So here, the P lambda is the polarization of lambda, and the cosine star is the theta star is the angle between the proton momentum and the lambda spin. And also, according to the SU6 wave function of the lambda, the strand quark or antiquark carries most of its spin, and therefore the polarization of the lambda reflects the polarization of the strand quark. And the DLL is defined in the PP collision is the ratio of the cross-section. The numerator is called the spin-dependent ratio, and the denominator is the spin-independent cross-section. For the spin-dependent cross-section, it can be factorized into the three parts. The first part called the pattern distribution function here. The blue, we call the delta F is the Helix distributions, and the delta sigma is the polarized partonic cross-section. This part can be calculated by the perturbative QCD, and the green part is called the longitudinally polarized fragmentation functions. So the DLL naturally links the Helix distributions and the longitudinally polarized fragmentation functions. And there are some theoretical studies on the DLL at weak energy. The left plot considers the polarization of the lambda with different parameterizations of the Helix distributions. As we can see, the different parameterizations give you some different lambda polarization. And the second plot shows you the lambda polarization as a function of the eta. Different scenarios of polarized fragmentation functions. And also it shows that the DLL can provide discrimination between different scenarios. And the right plot is the recent theoretical studies. It shows that measuring the DLL as a function of the jet momentum fraction carried by lambda hyperons can provide direct proofs to the polarized fragmentation functions. Here, similar to the second plot, there are also three scenarios considered. For example, scenario 1, consider only the strand quark can contribute to the lambda polarization. And the scenario 2, the UD quark also contribute to the polarized lambda, but with opposite sign to the strand quark. And scenario 3 is an extreme case that the UDS has the same contribution to the lambda polarization. And for DTT, its definition is similar, and also it's the ratio of polarized cross-section over unpolarized cross-section. The polarized cross-section can be factorized. Sorry, there is a typo. The polarized cross-section can be factorized into the transversity distribution, also the spin-dependent cross-section, which can be calculated by the perturbative QCD. And the green part is the transversely polarized fragmentation functions. And the right plot also is theoretical predictions on the D and N, which is slightly different to the DTT, but also the D and N shows that it is sensitive to different scenarios, the polarized fragmentation functions. These three scenarios are the same as I just mentioned for DLL. So for the measurement, and first we need to reconstruct the lambda, and they are reconstructed in the follow channel, and we applied some set of topological costs to reduce the background. In our measurement, this background is expressed at the level of about 10% under the mass peak. And for the residual background, we estimated with the sideband method, as I was showing on the plot. And these backgrounds are subtracted with the following formula, the bottom formula, and to correct the effects of the residual background. And the jet is reconstructed with the anti-KT algorithm, with the resolution parameter 0.6. And in addition to the TBC tracks energy deposits used in the jet reconstruction, the lambda anti-lambda candidates are also fed into the jet reconstruction input list, as shown in the cartoon. Here, the daughter proton and the pan are removed from the list, and the lambda are added to the list. And also the inject lambda are used to make sure that the lambda are originated from a hard scattering. And because of the detector effects, the angular distribution of the decayed proton is distorted by the detector acceptance, which is the detector acceptance. So in order to, in the measurement, we did not directly measure the polarization of lambda with based on this equation, but we measure the DLL in the small cosine theta beams, as the DLL is the spin transfer from the beam to the lambda, and also the acceptance is independent of the beam polarization. In a very small cosine theta interval, these acceptance are treated as a constant. So the DLL formula, which can be derived from the angular distributions in a very small cosine theta intervals, are extracted using this formula. So these formula are firstly used in previous published results, and in this formula, the acceptance will be cancelled. And the right plot shows you an example of the DLL as a function of the cosine theta star for lambda PT from 3 to 4. As for DTT, the extraction is similar, but the polarization direction is different along for the DLL. DLL is longitudinal direction, but for the DTT, the direction is shown as the right cartoon, that in the partonic scattering, the polarization direction of the scattering parton is rotated along the normal direction of the scattering plane. As we can see that SA is the polarization direction of the initial parton. Polarization rotated along the normal direction of scattering plane, and the final, the polarization of the final state of parton is FC. So the DLL, in the measurement of DLL, we measure the polarization along this direction, along the direction at C. But in practice, the z-axis is used as the outgoing parton direction. And the DTT is extracted using the so-called cross-ratio method with this formula. And this formula is firstly used in STAR previous published result. The right plot similarly also shows the DTT as a function of cosine theta star. So previously, STAR published measurement on the DLL and the DTT. The left plot shows the published DLL as a function of a hyperon PT using the data taken in 2009. This data set corresponds to the luminosity of about 19 inverse picobar, and some model predictions are compared with this measurement. And the second plot is the model calculation, which used the published DLL result as an input. And this result found that when fitting our published result, the result provide constraints on the string quark polarization. In the right plot is the published DTT measurement using STAR data taken in 2012. This data set corresponds to a integrated luminosity of about 18 inverse picobar. And currently, those measurements are statistically limited and are in agreement with the model predictions. And in 2015, STAR taking a larger data set for DLL and DTT measurement. These data sets are both the luminosity are both of about 52 inverse picobar. So with this data set, we can perform a very more precise measurement. And here is our measurement, the new DLL result. The left plot shows you the new result as a function of a hyperon PT, and this data set is more than twice statistics than the data set taken in 2009. And the second plot is the top panel shows you a comparison between previous published result, and we can see that these results are consistent with each other. And the upper panel of the bottom panel is we compared our result, combined the result between 2 years, and compared with the model predictions. And we can also see that they are consistent with each other. And in the bottom panel, we combine the result between 2 years and between lambda and anti-lambdas, and we found that our result strongly disfavor one scenario of the polarized fragmentation functions, which is the third scenarios. And this scenario use assumption that U, D, and S have same contribution to the lambda polarization. For the DTT measurements, the left plot shows the new measurement with STAR 2015 data. And also this data set is more than twice statistics than the data set in 2012. And we also compared with the previous published result, and they are consistent with each other. And when combined 2 years data, we found that at a high PT, the data is below to the theoretical predictions. This might indicate that the theoretical models overestimate the result. And according to the theoretic studies that as I mentioned before, the DLL and DTT as a function of the jet momentum fraction carried by hyperon can provide direct proof to the polarized fragmentation functions. So with this data set, we perform the first measurement of DL DTT versus Z. And in this measurement, we need to do a correction to the Z, namely from the detect Z to the particle Z using the embedding examples. Because in the jet reconstruction, the jet are reconstructed with TBC tracks and the energy deposit inside the EMCs. And it might miss some neutral part, or due to the detector acceptance miss something. So the jet momentum reconstructed using at detect level is not accurate. And in the theoretical calculation, we use all the particles to reconstruct jet. So in order to compare our measurement to the model calculation, correction was applied to the Z, the detect Z. And so in each detector Z beam, we calculate the average particle Z, and using the embedding example, and the differences between detect Z and the particle Z are treated as the correction and were applied to the data point. So, and this is our first measurement of DL and DTT versus Z, which provide direct proof to the polarized fragmentation functions. And the DL results are compared with the predictions. And currently, they are comparable to the model prediction. Also, we noticed that the measure result is small. This might indicate a small polarized fragmentation functions. So here it comes to my summary. In the analysis, we provide improved measurements of DL and DTT as a function of a hyperon momentum. And with the data set taken in 2015, and this data set extending the hyperon PT up to 8 GeV, and the statistics is more than twice than previously published result. We also applied the first measurement of DLL DTT as a function of Z. These measurements are believed to provide a direct proof to the polarized fragmentation functions. And also, we found the results are small, and these results might indicate small string polarization and or small polarized fragmentation functions. So that's all. Thank you.
Very nice talk. Any questions in the room? Looks like people need time to think. Then let's check Zoom. Any questions on the Zoom?
So while we're waiting, I could ask one.
Yeah.
Can you hear me?
Yeah.
Okay. So I had a question. You mentioned that you take the jet axis as the direction of the outgoing parton.
Yep.
Did you check that in simulation to see how accurate that is? Are you using the standard like anti-KT jet axis?
Yeah, we use the standard anti-KT jet axis. We also check the direction of using the lambda momentum. Two results are consistent with.
Sorry, but the first part was, did you check whether the jet axis is a good approximation for the outgoing parton?
we checked the, actually we did in the analysis, when correcting the Z, we need to match the detect jet to particle jet. So actually the 2D correlation plots of the momentum actually the momentum is, the size is very close, so it's the mean value is very close from detected jet peak and the particle. So we did not check exactly how the impact of this axis.
Okay, yeah, maybe I can talk to you about it offline. I'm a bit curious about it. Okay, thanks.
Okay.
Thank you, Isaac. I have another question before check again. So I have a question about your very naive question about your you're saying by doing the checking your slides. Let me check. New result should be slide 12, right? Yeah. So you exclude the scenario 3, where the scenario 1, 2, they are rather just S part contribute to the polarized lambda or S or UD in a different sign of S. But looks to my question is like looks to me the scenario 1, 2 are always very close, because they have the same sign in terms of DLL. Can we really separate them in the end? Because my question is like, for this is prediction, and the only difference is the magnitude of this trend, right? But if we compare the trend with the data, this looks like to me, it's very challenging to see which scenario is the case. But if naive understanding the scenario 1, only the S quark contribute to like not very logical. How do you think about this? Yeah.
The scenario 1 is according to SU6 a wave function of the lambda. So in the wave function, we know the only strand quark is polarized. So that's the why the scenario, how the scenario 1 comes from. And experimentally, we need to test, and also, but currently the statistics is not enough to separate to discriminate between the scenario 1 and scenario 2. So we currently don't know the scenario 1 if it is a logical,
I see,
or if it is the right assumption. So we can only test through by the experiments. So, but currently the statistics is not enough.
Okay. I also noticed that scenario 1 is like flat if we look at versus D, right? Well, this the evidence, if we found it's just consistent. Okay. Yeah. Thank you. Any more questions?
There was a question online.
Online?
Yeah, I have a very enough question. Can you hear me?
Yeah, please go.
Okay, so E, how did you determine the theta star?
Theta star example.
Yeah, what's the definition?
The theta star here is defined as the polarization direction of lambda and the momentum direction of the proton at the lambda rest frame. So in the experiment, we need to know polarization of lambda direction.
The spin direction of lambda.
Yes, spin direction is lambda. But so in the DLL measurement, we assumed it is along the longitudinal direction, which is the momentum direction of lambda. So we measure this direction, and for DTT, we measure the FC direction, this direction FC, along this direction.
So this SC is assumed to be the direction of lambda spin.
Yeah.
Is this
so
just
we
an
measure
assumption,
this,
or this is?
We measure its polarization along this direction. And in the Platonic scattering, it is the reasonable direction, because in the scattering, after the scattering, the polarization of the proton rotate along the normal direction of the scattering plane. So this is a reasonable direction.
Yeah, okay. Because I was wondering, how could you know the spin direction of lambda? All right, I get it. Thank you.
So it's we cannot know it exactly. We just assume it is whether it has a direction along this polarization along this direction in the experiment.
Mm-hmm. Okay, thank you.
Okay. More questions? We can have one more question if. Okay. If not, okay. Thank you, Yi. Very nice talk. Yin.